Welcome to this explainer. Today, we're diving straight into the brilliant parallel lives of two phenomenal scientists, Willard Libby and Leona Woods. These are two people who fundamentally altered our understanding of the world. We're looking at a story that marries the staggering, almost terrifying power of nuclear physics with the deep mysteries of our planet's past and its fragile future. These two incredible minds, they didn't just advance science, they built the very tools that allow us to basically see time itself. So, how did two atomic pioneers rewrite human history and uncover the secrets of our planet's future? I absolutely love this question because it perfectly bridges the dawn of nuclear weapons with the peaceful discovery of our ancient past. We often think of the atomic age purely in terms of destruction, right? Or maybe just energy. But as we're going to see today, the techniques forged in the intense fires of the Manhattan Project actually gave us an unprecedented lens to view everything, from human prehistory all the way to modern climate change. Section 1. The dawn of the atomic age. Let's rewind to the 1940s. It's a high-stakes era, and it's where our two brilliant protagonists began their monumental scientific journeys. The world was at war, and the race to understand and harness the atom was happening at breakneck speed across the U.S. Now, over on the East Coast, Willard Libby, who was already an established physical chemist, was at Columbia University unraveling this incredibly complex process of gaseous diffusion. Essentially, he was figuring out how to separate elements to create nuclear fuel. Meanwhile, in the Midwest, a young Leona Woods had just finished her PhD in chemistry at the University of Chicago. Utilizing her frankly incredible skills in vacuum technology and glassblowing, she was hired to build boron trifluoride detectors. These were used to measure neutron flux, the absolute crucial sparks needed for atomic reactions. So you have two brilliant minds working on two massive pieces of this giant atomic puzzle. Section 2. The Chicago Pile 1. At just 23 years old, Leona Woods was the youngest and the sole female physicist on Enrico Fermi's legendary reactor team. They were building the world's first nuclear reactor, literally right under the abandoned stands of the university's football stadium. But her incredible stamina went way beyond the lab. Laura Fermi, Enrico's wife, famously noted that to relieve Mrs. Woods of some work, Leona divided her time between atoms and potatoes. See, Leona's mother ran a small farm near Chicago almost entirely by herself. So after a grueling day of calibrating detectors, handling radium-beryllium sources, and basically building the atomic age, Leona would go home to help harvest potatoes. The sheer drive and energy she possessed at such a young age is, well, it's nothing short of awe-inspiring. When do we become scared? She bravely asked Fermi this haunting question as she stood by, again, the only woman present, when the world's first nuclear reactor, Chicago Pile 1, finally went critical in 1942. It was a completely uncharted frontier. Nobody knew with absolute certainty what would happen when a self-sustaining chain reaction was unleashed. Her question just perfectly captures the raw human emotion of standing at the threshold of a new era. And you want to know what's even more astounding? Just a year later, while she was still doing this high-level atomic work, she hid a pregnancy beneath baggy denim work clothes. She was vomiting on unheated army buses during her commute, simply because she completely refused to be sidelined from her critical research. Now that is dedication. Section 3. The Radiocarbon Revolution. Okay, so in the post-war era, Willard Libby arrived at the University of Chicago looking to merge chemistry and physics in a much more peaceful way. He was seeking groundbreaking applications for the radioactive isotopes he had studied so closely, and he discovered this elegant four-step process which allowed him to estimate exactly how long any organic organism has been dead. Let's walk through it together. Step 1. High up in the atmosphere, cosmic rays collide with nitrogen to create a radioactive isotope called carbon-14. Step 2. Living things, trees, animals, us humans, we breathe and eat, constantly absorbing this carbon-14. Step 3. The moment an organism dies, that intake stops instantly. And step 4. From that exact instant, the carbon-14 inside the remains begins to slowly decay at a predictable rate. Libby realized he had essentially discovered a natural stopwatch. 5,730. This staggering number is the half-life in years of carbon-14. It acts as a ticking biological clock for ancient organic matter. To put that into perspective, it means that if you have a sample of bone or wood and exactly half of its carbon-14 has turned back into nitrogen, well, you know that organism died exactly 5,730 years ago. Libby's team actually had to invent incredibly sensitive equipment just to detect this extremely faint, slow decay. They proved their whole concept by dating ancient Egyptian artifacts that already had known historical ages. And 60,000. This represents the maximum age in years that radiocarbon dating can accurately reach. After about 60,000 years, the remaining carbon-14 is just so minuscule that it can't be reliably measured anymore. But there's a major catch here. The sample must be meticulously cleaned. Because you're counting so few radioactive atoms, even a tiny speck of modern carbon, like a bit of dirt or just a fingerprint from a researcher, can completely contaminate the whole sample and throw off the age by thousands of years. Section 4. Rewriting Human History. Frederick Johnson famously said that carbon-14 dating had the impact of an atomic bomb on archaeology, and he was right. Libby's ingenious method won him the 1960 Nobel Prize in Chemistry, and it completely shattered how we view the timeline of humanity. Think about it. Before this, archaeology relied mostly on guessing ages based on the depth of buried items or the style of the pottery. Libby gave them hard, mathematical truth. Because it hit the field with the impact of an atomic bomb, scientists all across the world could suddenly compare the exact ages of settlements in Europe with those in the Americas or Asia. It created, literally for the very first time, a unified, synchronized global prehistory. Suddenly, we had a shared global timeline. Just look at this list of breakthroughs. Radiocarbon dating proved that Otzi, the remarkably preserved frozen hunker found in the Alps, died exactly 5,300 years ago. It allowed researchers to finally sync the ancient Mayan calendar with our modern one. It forced massive paradigm shift by proving that Australian Aboriginal history stretched back an astonishing 50,000 years. And it accurately placed some of the world's most famous artifacts, like the Dead Sea Scrolls and the Shroud of Turin, into their correct historical eras. It was an absolute game changer. Section 5. Environmental Science Pioneers. In 1967, Leona and Willard married and joined forces at UCLA to study our Earth's ecosystem. After distinguished separate careers, Leona had already published extensively in cosmology and high-energy physics, they shifted their focus from the past to the future of our climate. Together, they realized something profound. Because fossil fuels are millions of years old, they contain virtually zero carbon-14. Natural carbon sources, however, are younger emissions and contain abundant carbon-14. So when scientists measure the sudden massive spike of CO2 in our modern atmosphere and find that it severely lacks carbon-14, well, that is absolute, undeniable proof that this excess carbon is coming from burning ancient fossil fuels, not from younger, natural sources like forest fires or volcanoes. Leona Wood's Libby brilliantly utilized this concept, basically creating tree thermometers. She figured out how to extract ancient temperature fluctuations directly from the rings of trees using isotope ratios. By analyzing the ratios of different isotopes trapped in the wood as the tree grew, she essentially turned ancient forests into historic weather stations. This entire field, known as paleoclimatology, gives us the exact baseline data we desperately need today to understand just how rapidly our current climate is shifting compared to historical norms. Section 6. A Lasting Scientific Legacy. Their shared technical innovations definitely didn't stop in the 20th century. They laid the foundation for entirely new branches of science. Today, the radiocarbon revolution they sparked continues to save lives and map human biology. Interestingly, because of the spike in global carbon-14 caused by nuclear bomb testing back in the 1950s, medical researchers actually have a unique biological marker. They use it to track exactly when Alzheimer's plaques form in a patient's brain, or to observe at a molecular level how a new chemotherapy drug moves through a body, or even how a cancer tumor metastasizes. On a planetary scale, it even traces the deep movements of ocean water, which is absolutely vital for understanding global weather patterns and the complexities of geophysics. As we face a changing climate, how will the atomic tools built by Woods and Libby continue to unlock the mysteries of our planet's future? I really want to leave you with this provocative thought, reminding us that the secrets of our survival tomorrow are built on the foundations laid by these two incredible pioneers. Out of the terrifying, world-altering birth of the nuclear reactor, Leona Woods and Willard Libby managed to extract a profound gift, the ability to understand our past and rigorously measure our impact on the present. As we navigate the immense environmental challenges of our time, their legacy of atomic discovery remains one of our greatest tools for mapping a sustainable future. Thank you for joining me on this explainer.